Hi ladies and gentlemen, in this video we will see how LTI systems respond to weights and stationary stochastic process. So let me start with that presentation. The speech is organized into your learning outcomes. Mean of the output of the LTI system that is driven by a weights and stationary stochastic process. Then the autocorrelation of the output, we will derive this. Then we will derive the power spectral density of the output. Then the summary of understanding. So in this video, you will learn the response of LTI systems to WSS process. I apply an XT, that is a weights and stationary process, to an LTI system, and we see the response. Then we will compute the output mean, output autocorrelation, and output power spectral density. Now, LTI system is a system that is both linear and time invariant. A linear system is a system that is both additive and homogeneous. A system that obeys superposition theorem, that is a linear system, and a system that is both linear and time invariant, that is an LTI system. Probably you learn these things in detail in the signals and system course. Now here we see the effect of the response of LTI systems to weights and stationary stochastic process. When an LTI system ST is driven by a WSS XT, the output is YT, that is a convolution between the input and the impulse response. So that convolution integral is h beta xt minus beta d beta, or I can write as a h integral minus infinity to infinity ht minus beta x beta d beta. Both representations are correct. This is a self-same convolution integral. Now we have to compute the mean of the output yt, so that will be, because we are always interested in the first order and the second order moments of signals. So the mean of the output is mu yt, that is expectation of yt, so that is expectation of this convolution integral. So this expectation is happening over the random process. This h is a deterministic thing. This is the impulse response of the LTI system. This is a deterministic function. So the expectation is applicable to x only. So this integral becomes minus infinity to infinity ht minus beta expectation of x beta d beta. And this expectation of x beta is a dummy variable in terms of in place of t. So this expectation of x beta is mu x beta. So this integral is minus infinity to infinity ht minus beta mu x beta d beta. This is nothing but a convolution between h and mu x. So it is ht convolution mu xt. So the output mean of the output is mu yt is ht convolution mu xt. Now if my x is a WSS process, then this mu xt is a constant, that is mu x, so that mu y output mean is integral from minus infinity mu x times integral from minus infinity to infinity, because this is no longer a function of time. This beta is a dummy variable in time, so this is mu x comes out of that. So this is mu x integral from minus infinity to infinity h beta d beta. Now what is this function? This is nothing but the DC value of my frequency response. Because if you take the Fourier transform of ht, it becomes a frequency response of the system hf. For f equal to 0, this is integral h beta d beta or ht dt, that is nothing but capital H0. What is H0? This is a frequency response of the system at f equal to 0. So this is the DC response of the system. So mu y, that is equal to mu x into H0. So this is how the mean looks like. Mean of the output looks like. Now I'm interested in the autocorrelation of the output, that is RYY T1 T2. This is the autocorrelation of my output. That is nothing but expectation of YT1 into YT2. This is actually YT2. Expectation of YT1 into YT2. This is a small mistake here. Expectation of YT1 into YT2. Now YT1 and YT2 I put in terms of this function, this convolution integral, so that this becomes expectation of minus infinity to infinity h beta x t1 minus beta d beta minus infinity to infinity h gamma x t2 minus gamma d gamma. So this expectation happens over x values and not over h values. So it becomes integral minus infinity to infinity minus infinity to infinity h beta h gamma expectation of x t1 minus beta x t2 minus gamma d beta, d gamma. This beta and gamma are dummy variables. So what is this expectation of xt1 minus beta, xt2 minus beta? This is nothing but the input autocorrelation function. So this integral becomes, this value becomes minus infinity to infinity integral minus infinity to infinity h beta, h gamma. This is rx function, rx x t1 minus beta, t2 minus gamma, d beta, d gamma. This is the output autocorrelation function. Now what happens when xt is WSS is this rx function becomes a function of time differences. So rxx t1 minus beta, t2 minus gamma becomes, for a WSS it becomes rxx t1 minus t2 minus beta plus gamma. Okay, this autocorrelation is a function of the time shifts only. So this ryy t1 t2 or ryy tau, whatever it is, minus infinity to infinity minus infinity to infinity double integral h beta h gamma rxx, this t1 minus t2 I write as tau, then minus beta plus gamma. This is nothing but the difference between t1 minus beta and t2 minus gamma. This t1 minus t2 I write as tau, so it is tau rxx tau minus beta plus gamma d beta d gamma. This is the output autocorrelation function when the input is a WSS process. Now, if I take the Fourier transform of the last equation, this actually this ryy tau is also ryy t1 t2 is actually ryy tau. This is also a function of the time shifts only, because if the input is WSS, the output is also WSS. Now what happens is, if I compute the Fourier transform of this, I can compute the power spectral density, the output power spectral density SYYF. It is nothing but the Fourier transform of the output autocorrelation function. So Fourier transform equation, the self-same equation, I use minus infinity to infinity ryy tau e raised to minus j 2 pi f tau d tau. Here, after the first integral, I apply the equation for ryy tau. That's a double integral. This equation 4 I apply here. Okay, this equation 4 I apply here. This is this old equation 4 from here to here. Then e raised to minus j 2 pi f tau d beta d gamma d tau. Now I do some simple mathematical manipulation, so that first two integrals are h minus infinity to infinity minus infinity to infinity integrals h beta h gamma. Then I combine these things together. The last integral is minus infinity to infinity rxx tau minus beta plus gamma. So this rx is a function of tau minus beta plus gamma. So I make some slight modification in the kernel. Here I make it as e raised to minus j 2 pi f into tau minus beta plus gamma, so that these two arguments are the same. Now when I added this e raised to j 2 pi f beta and e raised to minus j 2 pi f gamma, I have to divide by that. So I added this division terms. This is a plus e raised to j 2 pi f beta, so I add a e raised to minus j 2 pi f beta. Here I added an extra e raised to minus j 2 pi f gamma, so here I added e raised to plus j 2 pi f gamma, so that the two added terms are cancelled off. Okay. Now inside this equation, this is what is this? This is nothing but the Fourier transform of rxx sum tau. Okay, rxx sum beta, whatever it is, tau minus beta plus gamma, which is nothing but sxf. Okay, this is my sxf, and I can split these integrals in beta and gamma, so that the first integral becomes minus infinity to infinity h beta e raised to minus j 2 pi f beta d beta, and the second integral is minus infinity to infinity h gamma e raised to j 2 pi f gamma d gamma, and this is my input power spectral density sxf. Okay. Now what is this? This one is nothing but hf. This is hf because this is a Fourier transform of h beta. Here it is h gamma e raised to plus j 2 pi f gamma, contrary to the usual equation for Fourier transform, when negative sign is missing. This makes it h conjugate f. Okay, if it is a conjugate, if I put an additional minus sign and a minus f here, this becomes h conjugate f. So it is hf h conjugate f into sxf df. Okay, so it is nothing but mod hf square sxf. hf conjugate f is mod hf square sxf. So this is the output power spectral density. If I integrate this output power spectral density, I will get the output power. Now, coming to the summary, you understood the response of LTI systems to WSS process. Then you derive the output mean, output autocorrelation, and power spectral density of an LTI system that is driven by a WSS. And that is the end of this presentation. I thank you all.